This mechanical energy is stored in tension. Stop. Start. Now let us see that one of the most important conclusion because of the surface tension is that due to the surface tension, a curved liquid surface, if the liquid surface is curved and that liquid surface is in equilibrium, then on that curved surface the pressure on the concave side is greater than that of the convex side. Right? If there is a liquid surface or the liquid surface is a curved surface like that, so we can say that the pressure on the concave side, this is concave side and this is convex side, so the pressure on the concave side is more than the pressure in the convex side. Now let us see that suppose if this is the case, right, if the liquid surface is a straight line, and let us say on this interface or on this liquid surface, here the pressure is P1, here the pressure is P2, so generally the P1 is equal to P2. But if the liquid surface is like that, a curved surface, so we say that if this is a curved liquid surface, this side is known as convex side and this side is known as concave side, right? So if P1 is the pressure on the concave side and P2 is the pressure on the convex side, so we can say that because of the surface tension, P1 is greater than P2. This P1 is greater than P2 and the difference between them, P1 minus P2, is known as excess pressure. This is known as excess pressure. Now let us see how this will happen, that the pressure on the concave side is more than the convex side. So let us derive a formula. In this we are considering an elemental curved surface. This is an elemental curved surface we are considering, in which the liquid is on the concave side. This is the concave side. So here this is the liquid and on the convex side we have gas, right? On the convex side we have gas, and we can say that this surface is assumed, this liquid curved surface is assumed to be curved on both the side with radius of curvature as R1 and R2, right? So this liquid surface is curved in both the side means, suppose let us say that this is one side, this one is this curvature and another one is this curvature, right? So the surface is curved on both the side, and one side the radius is R1 and on the other side the radius is R2. It is a 2D diagram, right? So we just represent it in 3D, that one is this curved surface and another one is this curved surface, right? This curved surface is of radius R1, this curved surface is of radius R2. You can see here this front curved surface is having radius R1 and this curved surface is having radius R2, right? And let us say that these curved surface will subtend an angle d theta 1 and d theta 2 at the center. At the center, angle subtended by this curve is d theta 1 and this curve is d theta 2. These are the angles subtended by them, and we can assume, let us say P1 or Pi is the pressure on the concave side and P0 is the pressure on the convex side. P1, Pi is the pressure on concave and P0 is the pressure on convex side. So we have to solve for it, right? We can say that the surface tension forces across the boundary lines, in this surface is like that. If we can see, suppose this is this R1 which subtend an angle theta 1 and this is R2, right? So on this, if I can say on this surface there is a surface tension force. Surface tension force is a line force, and that line is perpendicular to this. Line force is perpendicular to this. So we can say that on this d theta 1 we have a surface tension which is perpendicular to it like this, right? And this surface tension force is sigma into length, that is r2 into d theta 2. This is r2, this angle is d theta 2. So the length of this arc is r2 d theta 2, right? You know that length is equal to radius into angle subtended. So this arc is r2 d theta 2. So the surface tension force is a line force, and which we can say that surface tension is equal to force per unit length, and this length is perpendicular. So on this is perpendicular. So this curve is the perpendicular distance to this plane. This, we are calculating the surface tension on this surface, on this plane. So this is the length which we have to take into account. So this length is r2 d theta 2. So the surface tension force will be sigma into r2 d theta 2, where sigma is the surface tension of between this liquid and this gas. Surface tension between this liquid and this gas is sigma. So the surface tension will be sigma into r2 d theta 2. On this curved surface, if we can see from here, on this curved surface, this is the length which we have to take. This is the length. So this length will be r1 into d theta 1. So the surface tension force will be equal to sigma into r1 into d theta 1. Right. So if we can see that if I take this particular to resolve the components, if I take this is d theta 1, this is this arc, right? So we have the surface tension force sigma into r2 d theta 2, sigma into r2 d theta 2, and if we can project it, we can extend it, then this angle will be d theta 1 divided by 2. This is radius r1, and you just remember that we have to take r2 d theta 2. This curve is this one, right, which is subtended an angle d theta 2. So the surface tension force will be sigma r1 d theta 1 this side, sigma r1 d theta 1 this side, and this angle will be d theta 2 by 2. So these are the cases. So if we can say, if we considering the equilibrium of this small elemental fluid element, if we can say, if we consider the equilibrium, if you consider the equilibrium, free body diagram is we already make. So if you consider the equilibrium, we can say that the force balance in the direction perpendicular to the surface. Perpendicular to the surface. This is the surface. If we can make the force balance in the direction perpendicular to the surface, it will be, from this we can say, right, there is a two component of this force. This is sigma r2 d theta 2. It has having two component, horizontal and vertical component. This is also two component, horizontal and vertical component, right? Horizontal component will cancel each other, vertical component will add. So here we can say this will be equal to 2 times sigma r2 d theta 2, right? This is this force into sine of d theta 1 by 2 into sine of d theta 1 by 2, right? This is the force from this. If plus force from this will be plus 2 sigma r1 d theta 1 into sine of angle is d theta 2 by 2. These are the forces, and this will be equal to your pressure is there, right? Here the pressure is P1, here the pressure is P0. So I can write here, I can write Pi minus P0. This is the pressure. Force will be pressure into area. What is the area? This is the R2 d theta 2. This is R1 d theta 1. So the area will be R1 R2 d theta 1 d theta 2. So this is the free body diagram. This is the your generalized equation along the direction perpendicular to the surface. We are taking along the direction, this direction, right? This is the surface, this is the surface. We are taking in this perpendicular direction, all the forces we take in the perpendicular direction. So this will be the equation, right? So we can say that for the small angles, you know that for small angles, if the angles are small, then you can write sine d theta 1 by 2 as, it will be equivalent to d theta 1 by 2, and sine d theta 2 by 2 can be written as d theta 2 by 2, right? If I put this, so this will be equal to 2 sigma r2 d theta 2 into, this is d theta 1 by 2 plus 2 sigma r1 d theta 1 d theta 2 by 2 is equal to pi minus p naught into r1 r2 d theta 1 d theta 2, right? So from here, if you can see that from here, this d theta 2 d theta 1 d theta 1 d theta 2, these will cancel out, right? This 2 will cancel out, this 2 will cancel out. So from here you can write that if I divided it by r1 upon r2, if I divided it, so it will be pi minus p naught is equal to sigma upon r2 divided by r1 r2, this is r1 is left, plus sigma upon r2, right, plus sigma upon r2. So this is the case, and you can see that this equation is positive. This equation is positive. You can see from here that this equation is positive, and if this equation is positive, then I can write that pi is greater than p naught. Hence we can say the pressure on the concave side is more than the convex side, and this is known as delta P, which we can remember as excess pressure, which we can say as excess pressure. So the excess pressure will be equal to sigma upon R1 plus sigma upon R2. This is the excess. Start. So this is the excess pressure, delta P is the excess pressure, and Pi is greater than P naught, we already see. Now let us see the one more important concept here, right? If you see that in this case we discuss when the liquid surface is in contact with another liquid or another fluid or another gas, you can say, on the one side. That is, on the convex side we have gas, here we have liquid. But there may be the case when the liquid surface is coexist with, if I can write here, if the liquid surface is coexist with immiscible liquids or gases, you can say, on both the side. If we can say, if the liquid surface is in contact with liquids or gases on both the side, different liquids and gases on both the side, then we have two interface. Suppose here we have this, here it is liquid, here it is gas. It means that suppose this is the water is present here, right? This is the water. Suppose we have a beaker, and in this beaker we have this water. So this water, and here we have air. So we have only one interface. We have only this one interface. Then the surface tension will act here only, at one surface. But if the condition is like that, suppose we have a liquid layer. Suppose we have a liquid layer. This is a very thin liquid layer. Suppose you have, right, thin liquid layer you have. Let us say this is a water layer, right? Here we have air, and on this side also we have air. Now in this case you have two interface. One is this one, top surface, convex surface, and another interface is this one. Another interface is this one. So the surface tension will act here also, surface tension will act here also. So you have twice the force which we already solved. Then in this case, the pressure, the excess pressure will be twice of sigma upon R1 plus sigma upon R2. So you have to remember this. If you have two interface is present, then the excess pressure will be twice of this sigma upon R1 plus sigma upon R2. So these are the cases. Now let us solve for some special cases like your liquid drop, or you can say your bubbles, if you can say the air bubble, soap bubble. Then what are the surface tension act on that case? Let us see. So we have some special cases also. So this excess pressure is the phenomena of surface tension. And you remember one thing, that surface tension will depend upon the interface, right? As many interface you have in the system, so at each and every interface you have a surface tension force, right? So if you have the two interface, then you have two surface tension force acting on each surface, and it totally depend upon the interface, means that which two liquids or which two fluids are in contact with each other, the surface tension force will depend on that only, right? Now let us solve some of the special cases. Let us see some of the special cases. The first one will be your liquid drop. The first one will be the liquid drop. What is the meaning of liquid drop? We will explain, right? A liquid drop means that let us see that this is a liquid drop. Let us say this is a water liquid. Water is there. So inside you have water. Inside you have water. This is water. And let us say outside you have air. So this is the meaning of liquid drop. So we have only one interface, and in that case R1 is equal to R2, which is equal to R, right? Liquid drop, in the liquid drop the radius will be equal, all the surface radius will be equal. So in this case the excess pressure in the liquid drop will be equal to, if I can put here R1 is equal to R2, it will be equal to 2 sigma upon R. 2 sigma upon R, right? This is the liquid drop. So the excess pressure in the liquid drop will be 2 sigma upon R, and sigma is the surface tension between water and air, right? If these fluids will change, then surface tension will change. Now let us see that if the next will be your the excess pressure in the cylindrical jet, if I can say in a cylindrical jet, right? Over the pressure of surrounding atmosphere, we can say for a cylindrical jet. If cylindrical jet is there, cylindrical jet means like this. This is a cylindrical jet. Here the liquid is there, water is there, and outside we have some atmospheric air. This is the cylindrical jet. So in this case, we can see that in the cylindrical jet, when we can say that R1 will be equal to infinity and R2 will be equal to R. Why so? If you can see from here, this is the cylindrical jet. So this radius is R. On this surface, if you can see from here, this is radius R, and here we have the straight line. So the radius of the straight line is infinity, right? So don't confuse with it. It is a cylindrical jet like this. It is a cylindrical jet. So the one radius will be R and another surface radius will be infinity. So if this is the case, if you put here that R1 is infinity, so 1 upon or sigma upon infinity will be 0, right? So the excess pressure in this case, delta P, in this case, here also we have one interface. So to make you more clear, here we have one interface. Here also we have one interface. Right. So sig P will be equal to sigma upon R. So delta P will be equal to sigma upon R in the case of liquid jet, cylindrical liquid jet. So if we can say in the case of we can say that in the case of spherical bubble, right, soap bubble is there, right, if we can say the third case will be your soap bubble. Soap bubble. If you remember in the soap bubble, right, that soap bubble, like suppose this is a soap bubble. In this soap bubble we have this layer, this outer layer or this layer of the soap bubble is made up of some liquid, and here also we have air, here also inside it we have air. If you remember the soap bubble, when we are used to play in the home, right, that surf bubble we have, so inside also we have air, outside also we have air. So in this case we have two interface, one is this outer interface, another one is this inner interface. So in this case we have two interface, and if it is a spherical one, then R1 will be equal to R2 will be equal to R. So in this case the delta P will be equal to, we have to add it, 2 into sigma upon R plus sigma upon R. So the excess pressure in this case will be 4 sigma upon R. In this case the excess pressure will be equal to 4 sigma upon R. Just remember this, it all depends upon the interface. How many interface do you have, right? We can say that air bubble, if we can say we have an air bubble, right? Air bubble, if you see that air bubble, if you remember that in the liquid, if there is an air bubble, right, somewhere they will confuse you what is the meaning of air bubble. Not all the bubbles are of having two interface. Air bubble means if we have this liquid, let us say this is the water, we have this water and we have this air bubble, so here inside we have air, outside we have water, right? So only one interface we have only one interface. So in this case the excess pressure will be equal to 2 sigma upon R, not 4 sigma upon R. Don't confuse with it. If they are saying it is a air bubble, soap bubble is different. Soap bubble is made up of some fluid, that soap solution is there, that layer of that soap bubble is of liquid, and inside we have air, outside we have air. So we have two interface in this case. But in case of air bubble we have only one interface. Inside the air bubble we have air and outside we have water or some other liquid. So we have to use this formula to calculate the excess pressure, that is 2 sigma by R. So this is the surface tension, all the formulas and any numerical you can solve it with the help of these discussion. Stop. Start. Now let us discuss the another concept in the fluid mechanics, that is the capillarity. Before introducing what does this capillarity means, let us see what are the wetting and non-wetting liquids. Wetting liquids are those liquids when these liquids are in contact with any solid surface, they wet that solid surface. And non-wetting liquid means when those liquids are in contact with the solid surface, they will not wet that solid surface. So this wetting or non-wetting, whether the liquid will wet the solid surface or it will not wet the solid surface, it is a mutual property of both liquid and solid surface, right? In some of the cases, let us say if we can talk about water or let us say mercury, then there may be the case that mercury will wet one type of solid surface and it will not wet another solid surface. It may be the case, so this wetting or non-wetting is the mutual property of liquid and solid surface, and it will depend upon both cohesion and adhesion. It will depend upon both cohesion and adhesion. Cohesion means the intermolecular force between the liquid particles, and adhesion means the force of attraction between liquid and solid, right? So we can say if the adhesion is greater than the cohesion, right? If the adhesive force between the liquid and the solid is more than the cohesive force of the liquid, then it will wet the surface, then the surface will get wet. So if the adhesion is more, then surface will get wet. And for example, we take water on glass. If this is a glass on which water molecule is there, water drop is there, so it will wet this surface, and we can say this angle is theta. This angle is theta, and theta is known as contact angle. Theta is known as contact angle, and it is the angle between tangent of wetted surface, this is the wetted surface, and molecule surface. This tangent is between this wetted surface and this molecule surface, and this is the known as contact angle. And this contact angle theta is less than 90 degree for the wetted fluids, the fluids which will goes to wet the surface. In that case, this contact angle will be less than 90 degree. And for the special case, for pure water glass combination, if pure water is on the glass, then in this case theta will be equal to 0 degree. In this case, the theta will be equal to 0 degree. Another is when cohesion is greater than adhesion. When the force between the liquid particles are more than the adhesive forces, in this case the surface is non-wetted surface. Non-wetted surface. For example, mercury in the glass. If you put a mercury drop on the glass, then it will look like this, and if you draw the tangent here, the tangent will be like this, right? The tangent will be like this. So we can say this is the contact angle theta. So in this case, theta is greater than 90 degree for non-wetted liquids. For non-wetted liquids, the theta will be greater than 90 degree. So we can say that there are two types, that one is when the surface will get wet and another is when the surface will not get wet. Now let us introduce the capillarity. Capillarity is a phenomena in which when you have a tube, glass tube or any other tube, that tube is submerged in the liquid. If you submerge that tube in the liquid, then there will be either rise or fall of the liquid level in that tube, and this will depend upon the wetting or non-wetting behavior of the liquid, or you can say it will depend upon the cohesive and adhesive forces between the solid surface, the tube surface, and the liquid in which you immersed that tube. And this phenomena of rise or fall of the liquid level in the tube is known as capillarity. Right? So if we can write this definition, we say that capillarity is, this phenomena is when a tube of fine diameter, very small diameter, we will discuss it when we derive the formula for the capillary rise, why we take the fine diameter. When a tube of fine diameter is submerged in a liquid, then the liquid level, we can say the liquid level will either rise or fall on the tube, fall in the tube, you can say, fall in the tube, which depends on, this is the most important thing, which depends on wetting or non-wetting behavior, non-wetting behavior of liquid, or you can say it will depend upon cohesive and adhesive forces, cohesive and adhesive forces, and this phenomena is known as capillarity. This phenomenon is known as capillarity. So this is the definition of capillarity, right? You have to remember this, that when a tube of fine diameter, if you immersed in the liquid, then either the level will rise or fall, which depends upon the cohesive and adhesive forces, right? Which depends upon the cohesive and adhesive forces. So if I can say that capillarity is because of both cohesive and adhesive forces. Viscosity is because of cohesive, surface tension is because of both cohesive and adhesive, and same capillarity is also because of both cohesive and adhesive. So we can say if cohesive forces are greater than adhesive forces, if cohesive forces are greater than adhesive forces, the force inside the molecules or liquid are more than the adhesive, then the level will fall. And if adhesive is more than cohesive, adhesive is more than cohesive force, in this case the level will rise. In this case the level will rise, right? So if we can say that, if I can show it with the help of a diagram here, that what do we mean by this cohesive, adhesive, and the liquid level will rise or fall. Suppose you have this beaker, right? Suppose we have this beaker in which we have some liquid. Right, in which we have some liquid. This is the liquid here. This is the liquid. And in this, if I immersed a very fine diameter tube, if I immersed in this a very fine diameter tube, this tube I immersed in this beaker, right? And in this case, if we can say if the adhesive forces are more than the cohesive forces, or you can say if adhesive is more than cohesive, then the liquid will wet the solid surface. Liquid will wet the solid surface. In this case, the capillarity or the liquid level will rise. In this case, the liquid level will rise. Liquid level will rise. So in this tube, the liquid level will rise, and it will make this type of interface, and in this tube this liquid level will rise. So this is known as capillarity. This is known as capillarity, and this rise of liquid, this height by which this liquid will rise, is known as capillarity rise, and we will denote it with the help of letter H. We will denote it with the help of letter H. And we can say, okay, angle we will see it later on, but also, okay, if you remember from here that if I extend it like this, if I extend it like this, right, okay, angle we'll talk it later also. So if on another case we have this beaker, in which another liquid is there, some liquid is there in this beaker, right? This is the liquid level. In the beaker we have this much, and suppose if I insert a tube in this, right? If I insert a tube in this, let us say I insert this tube in this, right? I insert this tube in this, and if in this case the cohesive forces are more than the adhesive forces, cohesive forces are more, then we have non-wetted liquid. Liquid will not wet the solid surface, we have non-wetted liquid. So if we have non-wetted liquid, then the level will fall down. Level will fall down in the tube, right? So in this case, the level will be like this. The surface will be like this. Suppose here we have made this surface. The surface will be like this only. It will take this shape, and here we have no water here. The level will be here, but it will fall down in this case. So this height by which the level will fall is known as capillarity fall or capillarity depression, which we have to calculate in later on. So this is your capillarity fall, and this is the capillarity rise, liquid fall, right? If I show the angle, suppose it is not possible to show here. If I show it here for the capillary rise, for your better understanding, if you see that it will take this shape, right? So if I extend it in this direction, and this will be in this direction, then this angle is theta. This angle is theta, right? Similarly, in this case, we can show it here also. If I extend it like this and like this, so in this case, this angle is theta. This angle is theta, right? And we can write as that theta is the angle. Theta is the angle made by, you have to remember from where you have to take this theta. So theta is the angle made by, or you can say this is the area wetting contact angle made by the interface with the solid surface. This interface will make this angle with the solid surface, right? Angle made by solid surface with interface. So you have to take theta, in that case this one, and in this case this one, right? So this is the phenomenon which we known as capillarity. Stop. Start. Now let us discuss the expression for the capillary rise. Suppose this is the case of capillary rise in which adhesive forces are more than the cohesive forces. You know that this is the basic, that in this case the adhesive forces are more than the cohesive forces, and the liquid level will rise in the tube. Suppose the liquid level will rise. This is the liquid here, right? We have this, if we can say that this liquid we have which is of density rho. Rho is the density of this liquid. So let us say h is the height of the liquid which will rise, and here we have some air, let us say. Some gas is there, some gas will be there. So this is the interface. This is the interface of liquid, this is liquid, this is air. So on this we have the surface tension. On this complete we have surface tension, right? So surface tension sigma is the surface tension between this liquid and air interface. So surface tension sigma will act. Don't confuse that there are two forces. this is a cylindrical tube like this is a cylindrical tube like this, and you have the liquid surface. Suppose this is not this in this shape, let us say this is not in this shape, this is simple your horizontal. So this horizontal is there, this kind of surface you have. So on this surface complete at each and every point surface tension is acting, right? Because this is a 2D board, so we will show only the in 2, right? This surface, this sigma is acting on each and every point. This sigma is acting on each and every point. If you can see here, that sigma is acting on each and every point on the surface. Don't confuse it, there are two forces. They are not two, this is only one force which is acting on the each and every surface or each and every point on this interface, right? So we know that this angle is theta. This angle is theta, right? So if we can see from here, if we can say that under equilibrium condition, the horizontal component of these surface tension force will cancel out, obviously you know that. So we can say that the vertical component of surface tension force will be equal to weight of liquid column, right? You must remember one thing, that you must think one thing, that why this liquid will rise, right? And if the liquid is rising, which force is holding that liquid, right? Because of gravity, then it may fall, right? If this surface tension is not there, then because of gravity it may fall down. So some force must be there to hold it at this height h. So that is because of this surface tension force, it will hold this liquid column of height h. So in the equilibrium, the vertical component will be equal to the weight of this fluid, right? So if you see from here, what is the weight of fluid column? What is the weight of fluid? Weight will be density into volume. Density is rho. Volume will be pi by 4 d square into h. This is cylindrical. D is the diameter of this tube. This is the weight. And what is the vertical component? Vertical component of surface tension, right? Vertical component of surface tension is, surface tension force is a line force, and this line force is acting on complete circumference, right? On this complete circumference it is acting. So we can say the force will be sigma into, circumference will be pi into d. Circumference will be pi into d. This is the sigma, this is the force, and the vertical component will be cos theta. Vertical component will be cos theta. So if you equate it, so we can say sigma pi d cos theta will be equal to rho pi by 4 d square h. From here, this pi will cancel, this square and this d will cancel. So the capillary rise, height of capillary rise will be 4 sigma cos theta upon rho, one second, this will be 4 sigma, weight will be, this is mass, density into volume, this is mass into g, this is weight, okay, this is weight, right? So this will be equal to into g. So rho divided by g into d. Rho gd is left, rho gd. So the capillary rise will be 4 sigma cos theta upon rho gd. You have to remember this. It will be equal to 4 sigma cos theta upon rho gd. And if you solve for the capillary fall also, this is the same formula for both capillary rise and capillary fall. You can refer any textbook or any book or any notes for this formula of capillary fall. Will not solve it here, but the formula will be same. It will valid for both capillary rise and capillary fall, right? This will be 4 sigma cos theta upon rho gd, and you can see from here that height is inversely proportional to the diameter. You can see from this relationship that this height is inversely proportional to the diameter. If you increase the diameter very much, if the diameter of tube is large, then the capillary rise will be less. So that's why we can say that to observe the capillary rise phenomena, this diameter should be very, very small. Then only you can observe the capillary rise or capillary fall. So this is the formula for capillary rise, right? If we can say what are the examples of capillary rise, right? If we can say this marker is working on the capillary also. That ink which is coming on the nib is because of capillary, right? If you talk about candle, right, or there is a wick or oil lamp is there, that is working on the capillary only. Your gel pen, your ball pen, all are working on the capillary only, right? The roots of any plant which is taking from the roots water is coming to the leaves, that is because of capillary only. So the capillary phenomena will be everywhere. So all this thing is because of the capillary. Anywhere when a small diameter tube is in contact with the liquid, then either the capillary may rise or the capillary may fall because of the cohesion and adhesive forces. So this is the concept of capillary in the fluid mechanics. Stop.